She is our second invited speaker at this QWorld Quantum Science Days, and I'm very happy to introduce her to all of you. So she is currently a postdoctoral fellow at the University of Toronto in the group of Alain Asper-Guzik. And recently she has been doing some great work on near-term quantum algorithms. And she has also been involved in the development of computational tools for near-term quantum computers through this package called Tequila. And so her work is especially relevant to the kinds of things that people have been doing in QWorld. And I'm very happy to, and we're all very happy to have her speaking today about something that's, sort of keeping within the theme of variational computing. So she'll be talking about the meta-variational quantum eigensolver. So Alba, I believe you are here.
Yes, I'm here.
All right, nice to see you.
How are you?
Good, good. How are you?
Good.
All right, so maybe we can just start by sharing your slides, just to test all of that.
Okay, can you see my PowerPoint? Let me put the presentation mode. Okay, can you see?
Yep, it's good. All right, so let's, so we still have a few minutes, so I think we'll wait just so that we start on time so that anybody else who wants to join can join.
Okay, no problem. And thanks for the invitation. Unfortunately, I couldn't come earlier because I had other meetings, but I would like to stay longer after my talk because I see that the program seems quite interesting. So
right, yes, not a problem. So I mean, we will also, I think, are you on the Discord server?
Yeah, not right now, but yes, okay. I see that there is a Discord.
Right. So you should also feel free to answer questions that people might have. They might ask you their questions as well.
Okay. And the recordings will be available later?
Yes, they will be available later. Yeah.
Perfect.
And I should also introduce you, since we have some time, to Abu, who is our co-organizer or co-chair. It's also part of the program committee. So Abu, I don't know, are you there?
Yeah, hello.
Yeah. So he has put lots of effort and all the other program committee members into organizing this as well. All right, so let's a couple more minutes.
So Alba, you are in Discord server, yes?
Yes, not right now, but I see that there is a Discord channel.
Okay.
So Sumit just said that if people have more further questions, they probably answer us there.
What is your username? I guess it's not Alba, yeah?
No, I think it's just Alba Cervera Lierta.
Okay, I saw it.
Because I just entered the other day. I think it was yesterday when I was just trying things out.
Okay. I also give role invited speaker. So when you are online, people will see you separately also. Thank you.
Okay, so I guess we can start at this point. So Alba, take it away.
Okay, thanks, Sumit. Okay, hello everyone. Good afternoon or good morning, depending on your time zone. Today we'd like to talk about, of course, the meta-variational quantum eigensolver that we recently published, but I will just take the opportunity to also talk about other things that are related. For instance, what is a variational quantum algorithm, and also some tools that we develop for quantum machine learning, for variational quantum machine learning, that will be useful for the meta-VQE. So this is the, let me check if I can pass the slides. Yes, this is the outlook of my talk. So I will just start presenting to you Tequila, which is the package that we developed in our group 1 year ago or 1 year and a half ago. It's open source, so everybody can use it, and we hope that everybody contributes as well. So that's the main goal of Tequila, to grow and to develop more and more features. And then I will use Tequila later to program the meta-VQEs. In case that you want to check our codes, you will need to install Tequila first, but it's, as I said, publicly available and everything. Then I will summarize what is a variational quantum algorithm, because meta-VQE is in the end a variational quantum algorithm. And then I will introduce some tools that we will use for meta-VQE that comes from the field of quantum machine learning. So this is the outlook of the talk, and yeah, let's start. So first of all, Tequila, there is a white paper which is published in Quantum Science and Technology. You can also find it on arXiv. And the idea of Tequila is to develop, as I said, an open source quantum language that can be useful for different applications, for chemistry, for just quantum simulation, for playing with quantum circuits, etc. And the idea comes from this. So let me summarize the idea of Tequila in these slides. So first of all, as you may know, we are in the golden era of quantum languages, because quantum computing is also is a fancy field, and more people are joining us. And that means that we have basically different quantum programming languages for each quantum computer that exists in the world. So for instance, we have Qiskit that is developed by IBM, we have Cirq developed by Google, and so on and so forth, and many more. But not only is the golden era of quantum languages, but also of quantum software tools. For instance, we have many external libraries that help us to develop these algorithms. We have, for instance, QLabs, which is a quantum simulator. H4 or OpenFermion are chemistry libraries that are useful for quantum computing applied to chemistry. Meetic, which is a library to implement error mitigation, and many, many more. And on top of that, is also the golden era of classical tools for the NISQ era. In case that you don't know, NISQ stands for Noisy Intermediate Scale Quantum Computation, and this is the current state of the art in the experimental quantum computing. So we now have quantum computers, but they are noisy. That means that the operations are not perfect. We don't have quantum error correction yet, because that will require much more qubits. And we have quantum computers of the order of 100 qubits as much. That means that we cannot run all possible algorithms in real quantum computers, but we can just take advantage of the classical computation as well. And one of the examples are the variational quantum algorithms that I will present later. But the consequence is that we still need classical computation, and we also need classical computational tools. So for instance, we will need to mix together these quantum computing languages with other libraries that comes from classical computation, for instance, these optimization algorithms, libraries. So in the end, we have all these huge garden, let's say, of different quantum computing languages and packages. And the question is, okay, if we want to program with them, if us as a theoreticians, for instance, like me, I want to develop some quantum algorithm, which is the language that I should use? Because all of them are great, but what happens if I want to run an algorithm in one of the quantum computers, but then I want to compare it with another quantum computer? Then I need to write again all the algorithm to translate from one language to the other, but in the end, the code should be the same. So that was the idea behind Tequila. So can we try to automatize all these things so we don't have to learn over and over different quantum algorithms, or to translate our codes to different quantum algorithms? And that's the idea of Tequila, to unify and standardize all these algorithms. So Tequila works in a higher level. So it's a unified language that once we program with it, we just have to specify in a line of code what is the backend that we would like to run our quantum algorithm. So for instance, if we put backend equal to some of the IBM quantum computers, then Tequila automatically translates everything to Qiskit and sends the code to IBM quantum computers. Similarly, we can just change the backend and put some quantum simulator like QLabs, or introduce Cirq, which is the other quantum language for using Google quantum computers, and so on and so forth. So we don't have to care about learning what are the specifications of each language. Tequila just takes care of everything. And if you are interested, you can check the code in our group repository, and you can the installation instructions are there. And there are many tutorials, and we are just developing more and more tutorials as we develop more and more features. So this is let me just briefly talk about the Tequila API, how it works. So we normally in quantum computing, we start with some Hamiltonian or some operator that we want to compute the expectation value of this Hamiltonian because it encodes the solution of our problem. Then on the other side, we have some quantum circuit that in general, and especially for NISQ algorithms, it will depend on a series of parameters that we need to optimize and to find. For instance, the angles of rotational gates. So there are some ways to move from the operational form to construct the quantum circuit that solves this Hamiltonian by choosing a problem-specific ansatz. And for instance, some examples of these are the chemistry ansatz, such as unitary coupled cluster ansatz. And for that, we also need these external libraries that write down the Hamiltonian of our molecules in an operational form that we can use to construct the ansatz, and that we can use to construct the Hamiltonian as well. And Tequila, for instance, it has implemented automatically the unitary coupled cluster ansatz and other chemistry ansatz. So you just have to call it in a line of code. You don't need to know all the specifications of how to construct them. So once we have that, we compute the expectation values. And although these expectation values normally is enough for most of the problems, for instance, computing the ground state of our molecule, Tequila also accepts to construct a more sophisticated objective functions, which can be functions of these expectation values. So we can construct objective functions that are more sophisticated, and for instance, that will be especially useful for quantum machine learning, as I will present the meta-VQE as example. So then once we have this objective function, we just send it to a quantum backend. For instance, that could be a simulator or a real backend, as I said before. So now we currently support Cirq, Symbolic for Python, Qiskit, PyQuil, PennyLane, and also QLAX and Kibo. And to translate from objective functions to the quantum backend, we also have different options like noise or sampling if we want to simulate what happened, or you can also send it to a real backend. So you just have to specify which is your real backend or your credentials if necessary. So once we have the result, we normally, for these variational algorithms, we may need to optimize the parameters of our quantum circuit. For that, we also implement all these methods that comes from other external libraries like SciPy or GIOP or JAX or Phoenix, etc. And we also implement some particular minimization optimizers like the quantum natural gradient and others that are implemented also in Tequila, and more that are yet to come. Also in our quantum circuit, we also offer other options like wave function simulator, drawing the circuit, or defining the gates from Hermitian operators. So some gates are already programmed, like the standard control knot or Hadamard gate, of course. But if you want to define your own gate in the simulator, you can also do that by just writing down what is your Hermitian operator that defines that gate. And these are more or less the Tequila API, what is under the hood, but there are many other features. For instance, we also implement some other libraries like TensorFlow Quantum is also implemented in Tequila as a backend, also is integrated somehow. Also the X-zeta calculi that simplifies some quantum circuits, it's also mixed with Tequila, and we are working in more of them. So if you have any idea or if you want to contribute, just let us know, because we are happy to accept contributions for everybody. Just check our GitHub repository, or also if you find any issue, that will be also helpful. So the idea is that we develop as an academics this open source quantum language so everybody can use it, and you don't have to worry about if Qiskit changed something or Cirq changed some syntax, because Tequila will just fix that and implement that for you. So with that, we use Tequila in our current quantum algorithms. For instance, the meta-VQE is programming Tequila, and if you want to check the tutorial that we also wrote, you will need to install Tequila to run it, but it's very simple. So, okay, after this short introduction about this language, let me move to the scientific part of my talks. And I will start with what is a variational quantum algorithm in the first place. So as I said before briefly, we are now in the noisy intermediate scale quantum era, which means that we have the order of 100 qubits, and all of them are noisy, which means that they are not perfect. Each operation that we implement will have some error. The qubits are also doesn't have a very long lifetime, and that means that we cannot implement all possible algorithms. For instance, the Grover search algorithm, the short factorization algorithm, these kind of algorithms can only be implemented in fault-tolerant quantum computers, which means that they are perfect, and we are not there yet. So because of that, people just started to think what kind of things can we develop that still can be used in current quantum computers and fortunately have some advantage at some point. And as the previous talk already talked about some of them, for instance, the quantum approximate optimization algorithm is one of these examples of this NISQ algorithm. And it also belongs to this big family, which is the variational quantum algorithms that I will just briefly introduce now. So as I said, these variational quantum algorithms, some examples are the variational quantum eigensolver, the QAOA algorithm, and many more. The idea behind them is to mix the classical computation with the quantum computation. And that's why they are also called the hybrid quantum classical algorithms. So the idea is we start with some initial state that we know how to prepare in our quantum computer, for instance, by initializing all gates in the 0 state. And then this is the initial state enters into this quantum circuit that will depend on a series of parameters theta. So after we run this circuit, we have some output that, of course, it will depend on the parameters that we choose. And with this output, we compute the expectation value of our objective. Could be a simple objective like a Hamiltonian that encodes our problem, or it could be a more sophisticated objective like a collection of expectation values or any function that we would like to compute. So once we have this expectation value, the goal of the variational algorithm is to minimize it. So how can we do that? So we compute the gradients, or the gradients of this expectation value as a function of the parameters of this quantum circuit, and put everything inside of a classical minimizer that will suggest a new bunch of parameters to run the circuit again and check what is the expectation value with the new choice of parameters. So eventually, after repeating this process over and over, we hope to converge to a particular value, which will be a good approximation of our ground state energy that in the end tell us the solution of our problem. So this is the important parts here are the parametrized quantum circuit that I will mention now in the next slides. And then this bottom part, this loop that is classical. So as I said, these are also called hybrid quantum classical algorithms because part of the algorithm is run in a classical computer using classical computation. So in the end, it's the best of both worlds. So we compute with the quantum computer the hard part, which is the expectation value. But then we take advantage of all the tools that we know about optimization from classical computation to find the optimal parameters that deliver the ground state energy. So in the end, it's a matter of fine-tuning these parameters of our quantum circuit until we can obtain this ground state energy or the minimum of this objective function. So let's take a closer look of different parts of variational algorithms. The first is the objective function. As I said before, it could be just the expectation value of our Hamiltonian, or it could be something more sophisticated. But in the end, whatever we choose, it has to be decomposed into Pauli strings, because Pauli strings are the operators that can be measured in a quantum computer. So in the end, we start from an operator that is 2 to the power of n times 2 to the power of n, where n is the number of parties that we have, bigger, so exponentially big. And we decompose into a string that is, in best case, the goal will be to be a polynomial size. So in the end, we decompose something that is exponentially big into a sum of products that will be of polynomial size in general in most of the algorithms. So that's the first advantage of using a quantum computer in the end. So once we have this decomposed, we can reconstruct the expectation value of our operator by computing the expectation value of each of these Pauli strings. But an objective function can be things more different from just the Hamiltonian or some particular operator. We can also define it as a fidelity, which means what is the overlap between a quantum state and the state generated by our circuit. And that will be particularly useful for quantum machine learning. Then the other part of the variational quantum algorithms is choosing what is this parametrized quantum circuit. And this is one of the big problems because we need to define the circuit ansatz that will be parametrized, and we need to find the parameters of it later. So there are in general different strategies. We can group them in two of them. One is the problem-inspired ones, which means that we take our knowledge about our problem and we decompose it into a quantum circuit. And this is what is commonly used in chemistry using this unitary coupled cluster ansatz, or for instance, the QAOA algorithm, the quantum approximate optimization algorithm, also takes the problem and decomposes and translates it into a quantum circuit. And then we also have the hardware efficient ansatz, because the problem-inspired ansatz in some of the cases represent a very big circuits, which means that they cannot be run in current quantum computers, or not all of them, or not with the precision that we would like. So something that people just came out was, what about just choosing an ansatz that we know that it can be run in a current quantum computer by just applying these rotational gates and control nodes with the connectivity of the chip, for instance. And we repeat this layerized structure, and we hope that we have enough expressibility to find the ground state. Of course, it has its cons. It could be that the expressibility is not good enough, and it's not guaranteed that we will find the ground state. But on the other side, we can run it in a quantum computer. So of course, there is an active field of a study how to find these answers that are hardware efficient somehow, but at the same time, there is some performance guarantee that we will find a solution. And finally, the classical optimization part. We need to compute, if we use a gradient-based optimization algorithm, we need to compute the gradients of our quantum circuit as a function of each of these parameters, which means that in our quantum computer, we have to compute not only the expectation value of our objective function, but also the expectation value of all the gradients that we will need to optimize the objective function. So that's a lot of measurements. So obviously, even with this hardware efficient ansatz, or with any ansatz that we decide, the lesser the number of parameters we have, the better in this case, because if we have many parameters, this can scale really badly. And that's why some people also have developed other tools to compute these gradients by using the minimal number of measurements. So we reduce the computational cost, in this case, this quantum computational cost of these kind of algorithms. But this is also an active field of study. So this, I just put here the example of the parametership rule, which means that we can compute the gradients by just decomposing our unitary into small pieces. But this probably it's not even the most efficient way to compute the gradients. There are more sophisticated ones that reduce this computational cost, as I said. And then there is also some works that suggest they use other kind of optimization algorithms that are gradient-free, for instance, genetic algorithms or even reinforcement learning. So with that, let me just close this second part of my talk by talking about the variational quantum eigensolver, because I will use it later for meta-VQE. So the variational quantum eigensolver was originally proposed to solve, to obtain the ground state energy of molecules. And the idea is the following. We start with electronic structure Hamiltonian, decomposed into these Pauli strings. So these electronic structure Hamiltonians are written into using fermionic modes. That its fermionic modes represent, and operators, they represent the orbitals and the position in the end of the electrons in these orbitals of particular molecules. And what we do is we use some transformation rules like the Jordan-Wigner transformation that translate these fermionic operators into Pauli operators, or to spin operators, which are these Pauli strings and are the operators that we can measure in our quantum computer. So once we have our Hamiltonian decomposed into these Pauli strings, we need to obtain the ground state energy of this Hamiltonian. And for that, we can use the unitary coupled cluster ansatz, which takes this the Hartree-Fock solution, which is the most simple solution that you can obtain classically. It's like the first order approximation of the ground state of our molecule. And then we use the unitary the cluster operator to define the quantum circuit. And this cluster operator also comes from the Hamiltonian. So we decompose the Hamiltonian into the different excitations of the H4 orbitals. The more excitations we add, the more precise we'll be, but also our circuit will be much bigger. So it's a trade-off between these two things. And we need to find the parameters of this decomposition, and we will do that with the strategy of these variational quantum algorithms. So in the end, we also use here the fermionic operators to Pauli strings using, for instance, the Jordan-Wigner transformation. So everything is translated in the end into Pauli strings, and the exponential of a Pauli string is automatically translated into a gate that we know how to implement in our quantum computer. So in the end, the goal of the VQE is to minimize this energy as a function of these parameters. And this is related with the activation energy of our molecule, and that's why it's interesting from a chemistry point of view. Of course, this is just one of the examples. This, together with the QAOA algorithm, were the first variational quantum algorithms that were proposed back in 2014. And after that, many sophistication of these algorithms have appeared, and many, for instance, the meta-VQE in the end is just some evolution of VQE for a particular type of problems. And of course, people have used these variational quantum algorithms to apply them to other fields that are not chemistry, that are beyond chemistry. For instance, quantum machine learning, which is the next part of my talk. But before I go there, let me mention one big problem of these variational quantum algorithms, which is the barren-plateaux problem. As I said before, we need to compute the gradients of our circuit for each parameter that we have. And the problem is that if we don't have any prior knowledge about the solution, so we don't know what these parameters are, we normally start at random. So we just choose some random parameters and we start our optimization there. The problem is it has been proved that the expectation value of the gradients is exactly 0, and the expectation value of the variances is also 0. And this is related by the fact that the Hilbert space is so big, it's exponentially big. So if we start in a random place, basically the metric and the parameter space is flat, and we don't know in which direction should we move to find this minimum. And there are some possible solutions, and it is also an active field of study finding this solution or try to avoiding these barren plateaus. One of them is of course choosing parameters that are not initialized at random. So we have some knowledge about where is the solution, or at least the area of the parameter space. So we are starting close to that. Or using other kinds of cost functions. So instead of using just the minimizing a big expectation value, using local cost functions that only take a few qubits, or also introducing correlation between different parameters. So if the different parameters of our ansatz are correlated somehow, it has also been shown that we can mitigate or avoid these barren plateaus. But as I said, it's an active field of study as well, and there have been discovered this phenomena generated by other things, not only because we start at random, but also because we have too much noise or because we have too much entanglement. So it's an active problem, of course, that we need to avoid if we want to optimize our variational quantum algorithm, because in the end we can just get trapped in local minima very easily. So with that, let me continue with the third part of my talk, which is this quantum machine learning, variational quantum algorithms applied to quantum machine learning. And just to be clear, when I mention quantum machine learning, I'm mentioning an algorithm that is quantum. So we need a quantum computer to run it, and the data can either be classical or quantum. In our case, the data will be classical. So first, how can we move from classical to quantum neural networks? So classical neural networks, as some of you may know, we have some input neurons that has the parameters that we want to train. And these input neurons just feed the hidden neurons that process this information. We have some output, and with the output, we generate some loss function that will be used to update the parameters of these hidden neurons. So after we have trained our neural network, eventually we can just feed it with new data, and we will process it and obtain the final solution. Similarly, with this quantum circuit-centric quantum neural network, the idea is very similar. We will use some quantum gates to encode the data into our quantum circuit. We will use some gates to process this data, as the hidden neurons do. And then we will measure the state in our quantum computer. And with that, we will construct some loss function that will be used to update the parameters in encoding and processing. That's the general big picture. So some question that we had a couple of years ago was, what's the minimal quantum neural network? So what's the minimal needs that a quantum neural network needs to approximate any function? So first, what is the most simple but universal classical neural network? And the answer is just a single layer of neural networks. So there is a well-known theorem, which is the universal approximation theorem, that is known since the 90s, that as far as we have enough neurons, only one hidden layer is enough. Of course, this is normally not very practical because we may need a lot of neurons to approximate that function, and that's why we have deep neural networks. We divide this single layer into multiple layers. But technically, mathematically, only a single layer is enough to approximate any continuous function. So similarly, we ask the same question, but for quantum neural network. What is the most simple but universal quantum neural network? And we just proved that a single qubit is enough, providing that we apply enough operations. And this is the strategy that we developed. It was the last work that I did back in my PhD. And the idea is the same. So if processing goes from left to right in neural networks. And in this case, we have to fit each of the gates of our quantum classifier with the data. And we call this approach data reloading for the following reason. So how we encode the data in this single qubit classifier? We can use a product of unitaries, so we just have different quantum gates, and in the end, so we just modify the quantum state as if we were applying different neural networks. The problem is if we only use unitary gates that depend on parameters, and that's it, that's equivalent of only applying a unitary gate, because we can just put all together all these angles and redefine everything. So from a supervised learning point of view, if we start always in the same state, which is normally the 0 state, and we want to obtain a correct level, so we want to move to a particular state, we can just go there in a very complicated way or just choosing a direct path. But if we have another state, then the level is in another place. And of course, the path will be exactly the same because it doesn't depend on the parameters. So we will end up in a place that is not correct. So what can we do to fix that is to introduce the dependency somehow, of course, in our quantum circuit. That means that we introduce the data points in the circuit, and we call this a strategy data reloading because we apply the same data over and over in different layers of our quantum circuit. So the idea is that we just add this plasticity in our quantum operation. So this time the path will depend on the data X. And we prove that this is, you can find a one-to-one correspondence between the universal approximation theory of neural networks and this kind of model from a single qubit quantum classifier. But of course, this is just for one qubit. So one qubit can be simulated efficiently in a classical computer. So our goal that time was just to understand what are the minimal needs. But of course, that doesn't mean any advantage at all. It's just that a single qubit can do the same as a neural network, and that's it. So in a more general picture, what is these kind of strategies are called quantum feature maps. So it's finding the way that we can encode the data in a feature space that afterwards we can measure and we can estimate what is the loss function and update the parameters after that. So the idea is always the same. We have layers that codify the data, and then some processing layers that what effectively they do is rotate to the correct measurement basis, and then we measure in the computational basis as normally happens with quantum computers. And this is, again, an active field of research, how to find these feature maps, which feature maps are better and which ones work for particular example, which ones not. And for the single qubit classifier, I mention it because we will use the data reloading in meta-VQE. But it's only proof that works for one qubit. And we also run some simulations for multiple qubits, and it seems it works as well, but it's not proved mathematically. So with that, I have all the ingredients to move to the last part of my talk, which is finally the meta-variational quantum eigensolver, which was recently published last week in PRX Quantum. So the meta-variational quantum eigensolver, in the end, is a mixture between the quantum machine learning strategies of finding the feature map and everything that I just mentioned, and a variational quantum algorithm, as is the variational quantum eigensolver, obviously. And for that, let me come back to what is a VQE. What is the true goal of a VQE? Because I mentioned that, yes, the VQE tries to minimize the ground state energy, but that's not exactly true, at least not for the standard VQE. So the VQE, what we want, and as you can see, this is the original plot for the first paper of VQE. We do a scan. So we measure the ground state energy for different atomic separations. So that means that our Hamiltonian has one parameter, which is this atomic separation. And we check what is the ground state energy for each of these distances. And what we want to find is where is this minimum? So where is the minimum energy as a function of this atomic separation? But we don't even need to know all these parameters. We only need to know where is this minimum located. So we know what is the atomic separation, and we know what is really the minimal energy here. So in the end, we are just computing a lot of VQEs. So each of these blue points is an individual VQE, which means that we have to prepare our quantum circuit, run it, optimize it, computing all the gradients, etc., until we have this value. And experimentally the same, of course. So we will need to prepare everything and compute the gradients, etc., until we have this value. But we don't care about the atomic separation, what happens with the atomic separation at long distances, for instance, because we see now once we know the solution that this area was not interesting at all. So the question that we had is, can we try to do the same in a more efficient way, so we don't have to run as many points in our scan of this energy? Can we only identify these regions more easily? And the idea was to encode the parameters of our Hamiltonian inside of this quantum circuit, inside of the VQE. And this also comes from another example, which is an exact simulation of one of the Ising models. So in this case, it's a very simple example because the Ising model is a model that can be solved analytically. We don't need a quantum computer for that. We can do it by hand. But if you want to use a quantum computer, you can find what is the quantum circuit that prepares that. And once you find all the steps, you see that the parameters of the model, which is this lambda parameter and J parameter, are encoded only at the very beginning of the circuit in this Bogoliubov transformation, and that's it. So they appear somewhere. Of course, the circuit will depend on these parameters because this circuit diagonalizes solves completely the Hamiltonian. So we were thinking, can we try to do the same, but for a model that it's not solved analytically? So we don't know the solution as is in this case with Ising model, but maybe we can try to find it as using the strategies of quantum machine learning in the end. So can we prepare some quantum circuit that finds the correct encoding? So this is the outlook of the meta-VQE. We have some parametrized Hamiltonian, that these parameters could be the interatomic distance, or could be the transfer field, or it could be anything that is of interest in our Hamiltonian. And the goal is to find the circuit that encodes the ground state of the Hamiltonian for any of these values. So not only for a particular value, which will be an individual VQE, a standard one, but just in general. So finding a circuit that once we find the circuit, we can just run it and just changing the parameter of our Hamiltonian, which will mean changing a parameter in a particular quantum gates. So the standard VQE, the comparison is the standard VQE, we need to run individual minimizations for each of these points. And the idea of the meta-VQE will be to use only a few training points and then obtain this curve and identify the regions that are where the minimum is located, which are the interest of the VQE algorithm in the end. And to do so, we have this parametrized Hamiltonian, and we choose training points. So we choose some set of these parameters, but not 300 of them, only a few of them. And then we define encoding gates, and then some processing gates that depend on parameters. And then we will measure what is the expectation value for each of these training points. So once we have these expectation values, we put all of them together, and we construct our loss function, which is global in this case, to find the update parameters. So in the end, we have as many quantum circuits as training points we have, but the parameters of all quantum circuits are exactly the same, except the parameter of the Hamiltonian is the only thing that will change from one circuit to the other. So in the end, in analogy with neural networks, our parameters of these encoding and processing layers will be the weights and biases of our neural network in the end. The only thing that changed is the data that is encoding, but the weights and biases are the same for all the training points. And the same will happen here. So in the end, the output will be these optimized parameters of these weights and biases, let's say, for our quantum neural network. So then we have some different outputs. As the first, two different options. The first option will be to run the circuit with some test points and obtain the ground state energy profile. So once we have these optimization values, we can just use them, fix the quantum circuit, so we don't have to optimize it again, we don't have to compute the gradients again and all the process of variational quantum algorithms, but we just run it once and we compute the expectation value of it for a new parameter. And that's the idea of, that's what we call the pure meta-VQE. But we just found that this pure meta-VQE is still far from the exact solution. So it's not as precise. You can see clearly, and I will show you later all the benchmarks, that it can identify the regions where the minimum or the maximum is, but it's not as close as a standard VQE to the solution. So that's why we have another option. We choose these optimized points as a starting point of a standard VQE optimization. And we call that optimized meta-VQE. So instead of starting at random, as we will do in general if we don't know the solution, this time we start taking the solution of the optimized of the meta-VQE. So we have to minimize everything again. So it's as a standard VQE, we will need to compute the gradients to optimize the circuit, etc. But this time we don't start at random. And that will be will represent some advantages, especially with the barren-plateaux problem that I just mentioned, because since we are not starting at random, we are helping, or at least we are mitigating this problem with barren-plateaus, and we are not trapped in local minima as would happen in general with VQE. So this is so the idea in the end, the overall idea will be we run the meta-VQE with training points, we obtain these parameters. Once we have these parameters, we run it again with the test points, and we obtain the profile. Once we have this profile, we can identify the region that is interesting for us, for instance, a minimum or a maximum. And in this particular region, then yes, we run a more sophisticated, an individual minimization, which is of course costly because we need to optimize the parameters again, but starting from a point that is closer to the solution. So in the end, the result will be more precise than a standard VQE, and it will converge much faster because we are already close to the solution. So we benchmarked this idea with three different models. The first one is picking a model that we know is hard to find the ground state. And this is the one-dimensional XXZ spin chain. This model can be solved analytically using what is called as the beta ansatz, but there is no obvious quantum circuit of how to implement this beta ansatz. So it's not like the easy model example that I just mentioned before, that we know how to construct the quantum circuit. And also this model has two quantum phase transitions, which means that the ground state changes drastically depending on the value of this delta parameter. And on top of that, the ground state of the critical region of this Hamiltonian is highly entangled. So in the end, the ground state will not be obvious. It will not be just Hadamard gates or just a bunch of rotational gates. It will require entanglement, and it's not obvious how to generate this circuit at all. And also the energy profile, if you just compute it, it presents a peak in the region around lambda -1. So it's something that is not trivial, because imagine that it was just a line, so we don't know if we are actually learning something or maybe not. So this is the result for 14-qubit simulation with this transverse field equal to 0.75. So we only have one parameter to learn, which is this delta parameter that I just mentioned before. And the circuit ansatz is a hardware efficient one. So it's a layer of rotational gates and then layers of alternating control knot gates. And we use two encoding and two processing layers, which means that we encode the parameter into the rotational gates, the first two layers, and then the second two layers, we don't encode any parameter. It's just processing. So it's just some variational parameters that we need to optimize. And this is the result. As you can see, it finds the ground state pretty quickly with the product state because it's trivial, so it's easy to find this product state. But then for the entangled one, it's much complicated, as we were expecting, of course. But then if we take a closer look of what is the absolute error and compare different the meta-VQE with the standard VQE and with this optimized meta-VQE, we see that the optimized meta-VQE is the more precise one. And the difference is not as big. It will be more obvious in the other benchmarks, but we can start to see what is the advantage of using optimized meta-VQE. And as you see, the meta-VQE is far from the solution or farther than the other algorithms, but that's the thing that we were expecting. And in the end, it's a really hard problem because here the ground state is changing. So maybe we cannot use the same encoding in one part or in one of the phases and in the other phase. Probably we need to change the phase at some point. And that's why using this kind of strategies, which consist of learning what is the ground state and what is the encoding, we need to be careful with quantum phase transitions because the ground state will change. So probably our encoding also has to change. Then the next example will be a problem-inspired one, which is the H4 molecule using 8 spin orbitals in the STO3G basis set. And in the end, we also use this unitary coupled cluster ansatz, actually some variation of it, but the same idea, for 2 steps. And here we wanted to test 2 things. One is what happens if we use, instead of a hardware efficient and we don't know exactly how to construct the ansatz, etc., we use an ansatz that we know it prepares the ground state or something close to it, which is this unitary coupled cluster ansatz. And the other thing that we wanted to test is using 2 different kinds of encoding. So as I said before, we encode the parameter of our Hamiltonian inside of the rotational gates. And we use the linear encoding in the previous example. So similarly, we use this delta with some 2 parameters that we need to find. Here we also do the same. This time the parameter is the intermolecular distance, but we also use another encoding just to compare, which is these floating Gaussians. This other encoding contains more parameters that we will need to optimize. We went from 2 to 4 parameters to optimize. But on the other hand, we know that this kind of, the ground state of these molecules resembles these floating Gaussians. So we use all our knowledge about the physics and the chemistry of this problem to help the meta-VQE to find a solution. And we also test what happens if we compare it with a VQE, which initial state is the 0 state, or the initial state is the Hartree-Fock approximation, which is, as I said before, the first order solution of the molecule. So first of all, of course, the Hartree-Fock approximation works better because we are starting closer to what is the solution in the end. But then we see that the meta-VQE, it's even better than the VQE when the initial state is 0. But the optimized meta-VQE is better than the standard VQE. Not only that, but the nonlinear encoding much better than the other ones. This is very important because even if we have to add more extra parameters, so the cost could be slightly more, the error is much lesser. And this in chemistry is very important to go down to the lesser errors as possible because we need that particular chemical accuracy in the estimation of these energies. So in the end, it finds much better solutions because now we are using an ansatz that is problem-inspired, and the nonlinear encoding in this case is working really well because in the end we know that the ground state resembles this form. So we are just helping the meta-VQE to find this solution. And finally, this is the last example. We have this single-transmon simulator. So a transmon is the individual unit that we use to define to have the experiment of the experimental qubits in superconducting circuits. And you can find a way to map the Hamiltonian of the transmon, so how the qubit behave from an experimental point of view, not from an abstract point of view. You can map that into a quantum circuit and simulate it. So in the end, it's a quantum computer simulating another quantum computer. And we use this encoding that comes from this particular paper that is called QCAT mapping. QCAT stands for Quantum Computing Guided Design. And here we use one encoding and one processing layers. And this time we use different kind of gates. So we also wanted to try, first of all, a model that doesn't have a quantum phase transition, as was the case of the XXZ model. And on the other hand, another model that contains different kind of entanglement gates. So these are XX gates, also known as Ising gates, and they have extra parameters inside. So the control node gates are fixed. These XX gates, in this case, they have some parameters that we can also optimize. And we use, again, the linear encoding. And this time, the parameter that we want to learn is the Hamiltonian parameter, is the flux. So this is related of what is the energy of our transmon, which will be used to define the qubit levels. And here it finds practically the ground state energy in all cases, also the meta-VQE. But when we take a closer look of what is the absolute error, we see that the meta-VQE is still far from the solution in comparison with the others, although it can identify clearly this peak. So that's the goal of the meta-VQE in the end, to identify the interesting energy regions. And here we compare the optimized meta-VQE with the standard VQE, with VQE that we call a smart. So we take the parameters of the previous optimization to start the next one. So we are helping the VQE. So we are not starting at random all the time. And then VQE with encoding. So we also wanted to test if there was a difference between using optimized meta-VQE, which means, and VQE with encoding layers. So the only difference between VQE encoding and optimized meta-VQE is where do you start. You start with the solution of the meta-VQE for the optimized meta-VQE. You start at random or in the previous point for the encoding VQE. And we see again that the optimized meta-VQE is the best one. So in the end, the optimized meta-VQE is starting in a point that is much closer, apparently, to the solution than any other method that we use to compare it with. So the meta-VQE, although is not as precise as VQE, and we cannot use it individually if we really want some accuracy, we can see clearly that it helps a lot to find a more precise solutions once we run an individual optimization. So VQE has two advantages here. On one side, we can just identify what are the regions that are interesting to us. And on the other side, it provides an initial values that works better than the other strategies that we try to benchmark meta-VQE with. So with that, I'm just finishing. This is my last slide with some conclusions and overview of what I just said. Meta-VQE can be used to scan over Hamiltonian parameters and find these interesting energy regions, which is a very important feature that we will need for some of the variational algorithms. Not all of them will require that, but for the example of the VQE, we want to identify the regions of the Hamiltonian space that have the minimal energy. So we want to avoid to compute over and over different points that are not interesting regions for us. So in total, we will reduce the total computational cost because we are just avoiding individual minimization in parts that are not interesting. We can use the parameter solution of the meta-VQE to run a more precise minimization, and we call that the optimized VQE. And we check that the convergence is much faster because we are close to the solution. We are potentially avoiding barren-plateaux because we are not starting at random anymore. And we can avoid local minima, and this can be seen in this particular plot. As you can see, the VQE solution just jumps. Sometimes it's precise, sometimes it's not so precise. The optimized meta-VQE is much more consistent, and it goes down, and you can see that it's not getting trapped in local minima. And then finally, the encoding strategies of these VQE type algorithms may be useful to guide the optimization solution. And this is related with the barren-plateau problems that I mentioned before. One of the possible solutions of this barren-plateau problem is to add some correlation between the parameters of our ansatz. And this is the thing that we are adding here. We are adding the correlation is the parameter of our Hamiltonian. So it appears in different parts of the circuit. So there is some correlation here. Of course, we will need to benchmark this much more carefully to see if we are really avoiding barren-plateaux or not. And of course, we can use different strategies. We only use these floating Gaussians and linear encoding, but we can try many more. And there are many things that we can really try. But the goal of the meta-VQE in the end was to just prove how can we use the quantum machine learning strategies that some people are using for classification or for other kinds of problems, adapt them to the one of the first variational algorithms, which was the VQE in the end, to try to avoid and reduce the computational cost and the number of gradients that we will have to check and everything in the end. We wrote the code and demo in our, you can check it in this repository, and we use the Tequila package to run everything, all the simulator. We use the QLAX simulator, which was the faster one. And feel free to check and let us know what do you think, and try it in a real quantum computer if you wish. And yeah, that's it. So thank you very much. And thank you, of course, to my collaborators, Alana Spuruguzik and Jakob Kotman, which are the co-authors of this paper. And of course, all Tequila developers and the NIST review collaboration, which was quite a big. Thank you.
All right. Thank you, Alba, for this great talk. So we have time for some questions. There are some here, so in the Zoom chat, so I'll just go through them in order. So the first one is from Anuj, who is asking, does iterative layer VQE help to attend the challenges of original VQE?
Sorry, could you say that again?
Does iterative layer VQE help to attend the challenges of original VQE?
I'm not sure what does it mean with iterative layers, the layer-wise structure, or?
Yeah, I'm not sure.
Maybe if we can, if they can tap
the online, maybe we can.
I'm not sure if I understand the question. Iterative layers. Like the problem inspire, maybe the hardware inspire ansatz. They refer to that.
It's fine.
This is iterative layer. Iterative layer, when I say iterative layer VQE.
But what do you mean by iterative layer VQE? The hardware and the layers, so writing the answers as layers, or?
I think he was telling about linear solvers, iterative linear solvers in linear algebra, like Arnold iterations, Gaussian eliminations, such kind of iterations. It means.
I'm not sure if I understand. Sorry, I didn't hear you correctly.
No, the thing is, maybe I think he was speaking about linear algebraical iterative layer, like for Arnold iterations, Gaussian eliminations, and Hamiltonian iterations.
Okay, I'm not sure if I fully understand the question, but maybe we can, if you leave it in the Discord, maybe yes. I can clarify it there, because I'm not sure if I understand what do you mean now. Sorry.
Yes, we can continue that discussion on Discord.
Okay.
Yes.
Sorry.
Okay, so second question from Hitesh is, can we get a resource for quantum machine learning? So I think he is asking about any references that you might have on studying quantum machine learning.
Well, here I would just upload my slides, of course, so you can check it later. But here I put some references about the quantum circuit-centric classifiers and the original references actually that they suggested that. And then I also suggest the Penny Lane's tutorials. There are many of them in quantum machine learning. So yeah, that's a good resource, I think.
All right. Yeah. Okay, and this is one question that you kind of just touched upon at the end. Can you comment on how the correlation between the parameters and using local phase one can approach towards the solution, even if we don't have a good guess to begin with, under the barren-plateaux problem?
Yeah, I'm sorry, I cannot explain much about it because I'm not familiar with the details of this avoidance of barren-plateaux. So let me check where is the reference here.
Yeah.
Oh, sorry, it's at the end, sorry.
It's at the end.
So the idea is just, we didn't study barren-plateaux properly in VQE, as I said. It's actually something to be done afterwards, and it has to be done more carefully, of course. But we were aware that there are particular words like this one in particular. So if you're interested, check this reference, that they claim that you can avoid or mitigate barren-plateaux if you correlate the parameters. And I guess that I'm not familiar with the details, so maybe I'm not completely correct. But I guess that the intuition behind it is the problem of barren-plateaux is the Hilbert space is exponentially big, so you don't know how to move around. But if you start correlating different parts of your Hilbert space, because there are some parameters that relate one with the others, you are probably helping to instead of having a flat land, having something that resembles some minimum and maximum or some rocky, let's say, parameter space. And I believe that it goes in that direction, of course, from a more formal way, not only this intuition. But yeah, just check the reference, because I'm sorry, I'm not familiar with the details. And studying the barren-plateaux in VQE and really checking if we are avoiding them or maybe not, it's something that we would like to do in the future.
Yes. All right, good. One more question. One other one is, how does the optimal meta-VQE perform in noisy quantum circuits? Have you tried this?
Again, it is another thing that we didn't try, the noisy simulations of all of this.
Yeah.
Because also noisy simulations, there is another paper that says that if you have noise, you can also have barren-plateaux for other reasons, not for only initialization. So yeah, it's yet a different thing, and that will become much more complicated to analyze, of course. But of course, if you have noise, if you don't have a lot of noise, probably it's similar, because that's the idea of VQE algorithms or VQA algorithms, which is even if the angle is not perfect, so maybe we just solve it analytically and we found that the angle that we should put there is pi/3, for instance. If we have some noise, then our quantum computer is not applying exactly that angle, but something similar. But we don't care about the particular angles, because we will just find some solution, and the algorithm, the optimization algorithm, will just find these optimal angles that work for the particular quantum computer. But that's only if our noise is not super high. If we have a lot of noise, that doesn't matter anymore, and our variational algorithm will not work. And that's what other people just proved. Right. So, of course, you can implement this post-processing, which is these error mitigation techniques. But yes, studying the meta-VQE with noise will be a more sophisticated work. So maybe for a different paper, of course.
Yeah.
But you can play with it with Tequila if someone wants to play with that. You just have to define your noise model and see what is the solution, basically.
Right. So there's one final question that we can do quickly from Andras, who also posted it on Discord. So I think the first part of his question you've already answered, but the second part is, could you please compare Tequila to TCAT, a similar looking software package of Cambridge quantum computing?
It's actually very similar, because TCAT, as far as I know, they can also translate to different languages. So it's a matter of the features that it has. So, for instance, in our case, I'm not super familiar about TCAT, but we know that Tequila implements these chemistry external packages and also other optimization packages like the GuideOpt, which is for Bayesian optimization, etc. And the other thing is TCAT is closed source. It's not open source, as far as I know. Tequila is open source. So these are the other, to me, the biggest difference in this sense. So even if it's good and it's great, it's closed. So you cannot accept contributions for other people besides the authors and who they decide to accept. So that's why we wanted to develop Tequila as well. It's made from academia to academia as well, and it's open source, so anybody can contribute and check the code and improve it or find issues, whatever.
All right, great. So I don't know, Alba, if you're looking at the chat, but there's been a lot of interest in your talk. So what I will do is to ask those who have further questions to ask it on Discord. And I believe Alba is on Discord, so once she has time, she'll be able to answer your questions.
Yeah, will do. Thank you very much.
Yeah, it was great having you. Thanks for accepting our invitation. It was a great talk.